Section 4.3 is called just area. And what we're going to do is we're going to take what we know about area from middle school math and what we did last time where we put these funny summation symbols together, and we're going to kind of combine those two ideas. And then when we come back next Wednesday, not Monday because on Monday we're doing a quiz, but when we come back next Wednesday, we're going to relate this idea of what we're doing with area into what we did in the very first section with integrals. So Wednesday is like the culmination of finally we get to put all the pieces together. Okay, so we're still working towards that goal at this point. All right, so to start with, we're going to talk about the area of a plane region. So the area of this region, so when I say this region, what I want you to do is I want you to mark straight down here and then straight down here. And when I mean the area of this region, I mean the area of everything that's inside of this. So if you sort of somehow could figure out how to do this curving shape and all of this inside and get all this area, this is the area we're talking about. Okay, all of that. So what we're going to do in this section is we're going to approximate what that area is with rectangles. So I'm going to call that first location where I have my red line x0 or A, depending on which one you're looking at. So x0 is what I have on this slide right now. And then I'm going to call the last one x4. What I want to do is I'm going to split it into 4 rectangles. So visually speaking, we're going to divide this in half and then in half again. We're going to try to make the halves all look like half. And I'm just going to number these midway points. This is x1, x2, x3, x4. There is absolutely nothing special about doing this in 4s, except that it's easy to half and half again. So for the sake of doing a picture, this works pretty well for me to sort of show you what's going on. But again, could I do it with 5 or 7 or 15? Sure. I mean, we could do it with more. 4 is just nice. All right, so there are definitely, if we've done this evenly, then the width of all these rectangles, I know I haven't finished drawing in the rectangle, but the width of all these intervals is the same. That's kind of how I was drawing it or trying to draw it, is that the widths were all the same. So when we're talking about the area of a rectangle, how do we find the area of a rectangle? Yeah, it's length times width. So all of these widths are the same. But the length, or in this case, visually it looks more like a height, wouldn't be the same. Okay? Now, there are 3 ways, at least 3 ways, when you're doing rectangles to determine height. 3 common ways, anyway. One way of doing the height can be to use the left-hand endpoint as your height, which means the other way of doing the height might be to use the right-hand endpoint as the height. And the third option is to use the midpoint as the height. Those are the 3 ways that we're going to look at. So what I want to do is I want to do this same picture. I'm going to do the next slide, but we're going to draw it with left end points. So go ahead and draw your line straight down here, over here. We're going to half this interval and half it again, convincingly, or at least we're going to try. I'm not convinced, but I'm going to just be okay with it for the moment. And I'm going to label them the same way I did before, x0, x1, x2, x3, and x4. The widths are all the same, again, if I've drawn it properly and I'm calculating it correctly. And I'm going to use the left endpoint. So for this first rectangle over here, if I'm using the left endpoint, I'm actually going to use the point that's on the y-axis, correct? So it's going to look something like this. I'm sorry, not on the y-axis, on the x0, because that's not an interval. So I'm going to use the leftmost endpoint of this rectangle. So this is the rectangle I'm going to calculate. Obviously, this isn't a perfect approximation, right? It's going to be a little bit too much. I'm going to go on with that one. The second interval between x1 and x2, left end point would be this one. Again, when I use this left end point on this one, it's too much. I'm overestimating. But what happens between x2 and x3? I'm actually going to get an underestimate, like so. And between x3 and x4, I happen to get another underestimate. So because of the shape of this curve, this is probably going to be a pretty good estimate because I've overestimated a couple of them, I'm underestimating a couple of them, and it sort of convincingly looks like it's by about the same amount. Are you guys with me? So the widths are all the same, the heights are all different, and they're all determined in this picture by the left end point. So this is one way to do it. And we'll do one of these, an example with an actual function and stuff in a moment. Let's draw the same picture again, but use right endpoints, okay? So, drawing the same picture. You guys are old hats at this by now. This is your third time to do it. So draw the heights in here, halfway and halfway again, and label them x0, x1, x2, x3, and x4. Again, the widths are all the same, but this picture I'm going to draw it using the heights that are on the right-hand endpoint. So the interval between x0 and x1, the right-hand endpoint is actually at x1. So that's the height that I'm going to use for that instead. So we have this as my rectangle over here. And this time, that's actually an underestimate, isn't it? And it's actually a pretty considerable one. I mean, it looks like a pretty significant underestimate. The next one, between x1 and x2, the height would be actually at the x2 value, right? It would be right here. It would cut across like that. Again, another underestimate. Between x2 and x3, at x3, right? And we come straight across. This one ends up being an overestimate. And then the last one, between x3 and x4, I'm at x4, and this one ends up being a significant overestimate. But again, because of this particular curve, it kind of looks like the overestimates and the underestimates might be leveling themselves out. Now, this is sort of dependent upon this curve. I mean, if the curve didn't look like this, it might be that we overestimated every single rectangle or underestimated every single rectangle. So I don't want you to think that the overestimates and underestimates always even out. They don't. It just depends on the curve that you're looking at, okay? There is a third option. We don't have to do left endpoints and right endpoints. We could do midpoints. So I'm going to do the midpoints, and then we're going to go back to the last two, and I'm going to actually put some formulas to what we're doing. So right now we're just working on the picture part of this. All right, so this picture should start out the same, right? We're going to draw the heights of the rectangles. Or, I'm sorry, we're going to draw the intervals actually first. Split my interval up into 4 pieces. But what we're going to do is we're going to find the point that's halfway between each of the end points. So if I'm at x0 and I'm at x1, I want to be halfway in between at that value. So I'm just going to mark them on my x-axis first, down here. These are the midpoints. But I want to be on the midpoint at the height that I'm at. So for instance, if you imagine sort of dotting this up here so you can see where you are, you're about right here. All right, so the height right here would be about right here. Halfway would be about right here. And halfway would be about right here. Something like that. Those dots that I have put along the function itself, that curve, that's the place where I'm going to make my height now. So that's going to be my demarcation of my height. So I'm going to have something looking like this. And like this. This and this. So again, on this curve, it kind of looks like in each of the individual intervals, I'm getting a little bit of an overestimate and a little bit of an underestimate. So again, maybe it's sort of evening out. Some functions that will work for better than others. Again, some functions it'll still be predominantly an overestimate or an underestimate. But this is the area that we would actually be calculating if we calculated the area of the rectangles instead. Okay, I'm going to go backwards now. So flip back to the front page of your notes, and we're going to go back and take a look at those left-hand endpoint ones. And we're going to talk about actually what it looks like when we calculate the area. All right, so whatever this distance is, we talked about it being the same, right? This distance and this distance, they're all supposed to be equal if we've calculated them correctly. Agreed? So we're going to call this distance delta x, which just means the change in x values. Right, like when you did slope, delta y over delta x. Okay, so this just means a change in the x values. And so what I'm supposed to be doing is I'm supposed to be calculating area. So what does that look like? Well, I want the area of each of these rectangles. So let's look at the very first rectangle. It has, you all told me that the area is length times width. We know the width is delta x. What is the length or height of this rectangle? I don't mean a number. We don't have any numbers on this graph. But how would I figure out what the height is? Okay, not the y-axis exactly, but so what do you mean by distance?
Like, to get the distance between x0 and that point up there.
I think you mean the x-axis in that point up there, not x0 specifically, right?
Yeah.
Okay, so we want to actually know the distance between the x-axis and the height where we're at, correct? Well, but how do I find the height? Isn't it just this particular point? So how do I figure out what that particular point is on the curve? I mean, I know it's at x0, but that's not the value I want. I want the height value, which would be the y value there. So how do we calculate a y value at a particular point? Generally speaking, what do we do?
Put it in an equation.
You put it in an equation, all right? So let's give this function a name. We'll call it f of x so that we have an equation to plug it into. But this point right here would actually be at a height of f of x0. Right? It's the function value, the y value at that particular x value. So up here I have my length, which would be the f of x0, times my width, which would be delta x. What about the second one? Second rectangle. What would its height be? F of x1. And its width, delta x. What about the height of the third rectangle? F of x2, you're correct, times its width, delta x. And the fourth rectangle, f of x3. And its width, delta x. Now you can actually use this formula exactly like it is right here, but there's a way to make the formula a little bit easier to do too. Any ideas on what that might look like or be? Yeah, if you notice, there's a delta x in every single term. I could just do the delta x multiplication at the end by factoring it out. Then all I would need to do is I would just need to add up 4 y values, f of x0, f of x1, f of x2, and f of x3. Notice there's no f of x4 on this one. Why not? Yeah, because we're using the left-hand points, right? And an x4 is actually on the right-hand side of the last rectangle, so it doesn't end up having a height used there. So this is what we're going to tend to be using. It's easier to work with. It's just fewer steps for finding the area with left-hand endpoints. We're going to find the 4 or 6 or 12 or whatever y values. We're going to add them together, and then we're going to multiply by the constant width of every single rectangle. Let's use this same idea and come up with a formula quite similar for right endpoints. What would be different on this formula? I mean, they all still have delta x's, right? What's going to be different? You're going to use x4 instead of x0, right? So we're sort of just shifting what values we're using on the y-axis, correct? Or what y values we're using. So my area on this will be the delta x, and it will be multiplied by the sum of these x or y values, but the y values will start at x1 instead of x0, and they'll go all the way over to x4 instead of stopping at x3. And again, there's nothing special about 4. It's just easy for me to draw a picture for you and see and establish what's going on, okay? Midpoint is more complicated to process because we don't have names for these particular points. It's not x0, it's not x1, it's somehow halfway between, right? But we still have the y values here. So let me just call them y1, y2, y3, and y4, okay? We tend to actually have to find those individually because they're not typically given to us. But I still calculate the area the same way. I have delta x times the sum of the 4 y values. Okay, it's just that the y values are coming from the midpoint instead of from one of the end points. All right, so we're going to actually find one of these now. All right, we've actually got a function, and we've got numbers. I know, some of you don't think math is math if you don't have numbers, so now you've got some numbers. And you've got an equation, so f of x equals 2x squared plus 5. It's a pretty simple equation, parabola, right? We're going to go from 0 to 2, and we're going to use n equal to 4. All right, so we are going to have the 4 rectangles like the 4 that we just talked about in the last examples. But we're going to do this problem 3 times. First time using left endpoints. Second time we're going to use midpoints, which I might actually do these out of order, so you can forgive me in advance. And then the third one is actually right endpoints. This is how your book writes the directions down. Okay? But if we've really already found the left endpoints, it's a very slight change to find the right endpoints. So, yes.
Have to draw it.
Do you have to draw it? You don't have to, but it might help you to see it. It's up to you. So am I going to grade on the fact that you drew it or not? No. If you don't want to draw it, that's okay. Or if you just want to graph it on your calculator to give yourself a reference without putting on your paper, I'm fine with that. Now, I am going to draw it because I think, at least for us having this discussion, it's helpful to see a picture. This is a parabola opening how? Up. What is its y-intercept? 5. The plus 5 at the end tells us we shift the whole thing up 5. So this is actually starting at 5. And then it's opening upward from here. So it looks something like this. We got half of a parabola anyway. That's actually the vertex right there at the bottom. Now, it's important to realize that when we're drawing these rectangles, if I draw with a left end point, what's going to happen? In fact, you know what? Let me mark this on the x-axis before I do that. So we're going to go from 0 out to 2. So we'll call this 2. I don't know if my scale's quite right on the y-axis or not. It probably isn't. But we'll use this as our visual anyway. We're not justifying our answer from it, just giving us a visual. We're going to cut it in half, which means my midpoint's actually what? 1. And then we're going to cut those at half again. So what are my midpoints of those? Right, 1/2 and 3/2. Or if you want to use decimals, you can use 0.5 and 1.5. So either fractions or decimals will be fine. And so my rectangles are going to have these particular places that we're coming from. Those aren't perfectly straight, but they're not too bad. All right, so let's think about what happens when we use left endpoints. When I use left endpoints, I don't want to draw it because then I'm going to mess up my picture for the other pieces. But if I use left endpoints and go across here, what's going to happen?
It's going to be all underestimated.
They're all underestimating because that's how this function particularly works. What happens if I use right endpoints and draw them from that way? They're all overestimating, okay? So this is one of those really good examples where one direction does one, the other direction does the other. And then what happens when I do the midpoint? It should be really good, right? It's going to feel like I've got some overestimate and some underestimate in every single interval. So the midpoint is what we're going to be sort of benchmarking our success on. We think that this is going to be the right value, okay, or closest to the right value. All right, so part A says that we're going to do left endpoint, so I'll do that part at least in order. So using the left endpoints for my area, in fact, using all of the endpoints for my area, I need to know the width of each of these intervals. So what is my width? That is, what is, I think I got too many of those going on there. I do. What is delta x in this particular problem? 0.5. Everybody good with that? So I've got 0.5 here. And then I'm supposed to have 4 rectangles, so I should have 4 y values, correct? And the y values for the left endpoints mean that what is my first y value that I'm going to be using? At what x value? At the x value of 0, right? Which is a y value of 5. What I'm going to do right now is I'm just going to write it in like the notation was that we had before. It's f of 0. Because 0 is where I started the interval, and I'm using that endpoint from the left. What about the next one? What would be the next x value that I use? I'm going to f of what x value? 0.5, or 1/2 if you're using fractions. How about the next one? 1. And I need one more, and it's at 1.5. I expect to see that equation written down. What you do after that, you have some options of. I'm going to show you one more step that's sort of, you can write it if you would like to. I'm going to actually figure out what each of those individual x values are and write them down. You can find out each individual x values in your calculator and do it too. So if you have your calculator with you, I want to show you how to do some cool stuff with it. I can't imagine that I've shown you all of these details before, but I may have shown you pieces of this. In fact, I know I've shown you pieces of this. I'd like for you to take your y equals menu and to put this equation in, 2x squared plus 5. So you should have y1 equals 2x squared plus 5. Does everybody have that? Fabulous. So go back into your regular blank screen. Okay, we're not in any tables, we're not doing anything special, just regular blank screen. I want to know what is f of 0. Okay, I know it's 5. We can do that very quickly, but just for the sake of how we do the operation of calculator, what do we do? Well, do you remember when we were using some of this stuff before and I showed you how to pull up y1? I think I've done that before, where you hit vars. Okay, maybe not. Maybe I'm remembering a different semester or a different class. There's a vars button. It's underneath your keypad that looks like all the arrows. It says VARS. Vars stands for variables. So select that one. We want a y variable because we've stored this in the y equals menu. So arrow over to y vars. This is a function, so we're going to select number 1, function. And we stored this into the equation y1. So we're going to select y1. So right now on your blank screen, it should just say y1. Don't press enter yet. That's what it should say. So that's kind of like the notation where it says f. F doesn't mean a lot without the value next to it, just like the y1 isn't meaning anything in the calculator right now without a value next to it. So put a parenthesis, 0, end parenthesis. So in your calculator right now, you should have something that looks like y1 of 0. Does everybody have that? And now we all know that when we hit enter, it should say 5, so let's check and make sure it does. Did it work? Excellent. y1 of 0 is 5. Okay, so whether or not you write these pieces down, I'll show you another way to do it in a moment. We're going to write it all down together on this one, and then I'll show you another option. You can actually go back through all that same again. So you can hit vars, arrow over to y vars, select function, and then y1, and put y1 of, not yet, 0.5 or 0.5, right. So now your screen should actually say y1 of 0.5, or 1 over 2. What value does that give you? 5.5 is correct.
Can't you just put in the table?
Yes, you can. I'm going to show you something else with this in a minute, though, that helps to see it from the screen. So just bear with me. You're right. You can do this from the table. There is one caveat to doing it from the table that's not especially helpful. Let's say, for instance, this ends up being a repeating decimal or something like that, and maybe it's even a repeating decimal that you don't know what the value is. From this screen that you're in right now, you can turn it back into a fraction. It's a lot easier to work from a fraction point of view than it is from a repeating decimal point of view. So if you're in this screen, you can hit math and hit it back into a fraction without it having to stay as an ugly, strange-looking decimal. So there is a nicer feature to this that allows you to do that. There's actually another reason I'm going to do it for you from this perspective too. All right, let's do f of 1. So vars, y vars, function y1 of 1. So parenthesis 1 in parenthesis. What value do you get? 7. We've got one more to do, f of 1.5. So what is f of 1.5? 9.5? Fabulous. All right, so grab your calculator, add together 5 plus 5.5 plus 7 plus 9.5, hit enter, and then put times 0.5. What do you get? 13.5. All right, so now let me tell you what the benefit is to actually using this screen from a very practical standpoint instead of from this sort of odd example of fractions and repeating decimals that I mentioned before, which is true. It's just not the real reason why I like using this screen. I told you you could find each of these 4 values and write them down, but I also told you that that's sort of an optional thing, right? So what if you didn't want to do that? What if you just wanted to go from the first line here to the last one? Well, your calculator can do that, right? So you can hit, in fact, I'll do the 0.5 part of it at the end, the multiplying by 0.5, just so I can eliminate some of the parentheses I'm going to have. We can actually tell the calculator y1 of 0 in parentheses plus y1 of 0.5 plus y1 of 1 plus y1 of 0 or of 1.5. We can do it all on one line. So let's give it a try. Grab your calculator, and I want you to do y1 parentheses 0 plus. So don't hit enter, hit plus. And then do y1 of 0.5. So vars, y vars, all the way through there to do 0.5. Plus vars, y vars of 1 plus, one more time, of 1.5. And if you do that, you can hit enter, which is going to give you everything inside the parenthesis right now, and then you can hit times 0.5. So all the calculations are done without you finding any of the individual pieces, which saves you time, right? So that's actually the real reason why I like using this particular screen instead of a table. It still gets me 13.5. Did everybody's work out okay? Get all your parentheses in there and everything, okay? Now here's the cool reason why I like this. 2 lines up in your calculator now, you have this notation, y1 of 0 plus y1 of 0.5 plus y1 of 1 plus y1 of 1.5, right? I mean, you have that in your calculator. Don't clear anything, just leave it sit there. If you've already cleared, you're still okay, but just leave it sit there for a second. We're going to skip part B, we'll go back to it, and we're going to do part C and find the area. So we need to write it down first. That I want to see. The width of all these rectangles is still 0.5. That didn't change. But what are the different what are the different x values that we're calculating the heights at this time? We're going to start at f of 0.5, right? And in f of 2. So this is f of 0.5, f of 1, f of 1.5, and f of 2. All right, so this is one of, I don't know how many years I used the calculator before I knew this feature, so maybe you're in the same boat as me. I would like for you to grab your calculator and hit second, enter, and tell me what happened when you hit second, enter. What happens when you hit second, enter?
The little thing pops up like the same thing.
Yeah. It brings up the previous entry. If you hit second enter, it should look exactly like the line before. Does it? Okay. Does everybody else's? Can I look at yours, Ruby?
Oh, I just gave all the answers.
Okay, you haven't put in. I told you to do this.
I did.
That's where is it?
I interned did that. I don't know why.
When you put those in?
Yeah. I hit second.
And you typed those in?
Yeah.
Okay, let me take a look at your calculator after that. I've never seen you do that. Okay. But what I want you to do is I want you to hit second enter a second time. What happens when you hit second enter a second time? No one's talking. Did it do anything? Tristan, what did it do?
It was to like one more.
It went one line up from that, did it? Does your screen now say y1 of 0 plus y1 of 0.5 plus y1? Does it say that now? I need feedback. Edgar, does yours, you have a different calculator. Matt, does yours say that?
No, but maybe it's because I added everything and then I did the answer times 0.5.
In the same list?
No, like I pressed enter after adding it and then I multiplied that answer.
No, that's fine. Damn it. Calculators today are stressing me out.
That's
Mine's working just fine.
All right, we're gonna hit second enter a second
That's
time.
complicated.
That's what I want to show.
oh.
Okay. All right, so everybody, what about over on this side of the room? Are your calculators going to stress me out? Is yours showing the right thing? Fabulous, that's exactly what it should be showing. Okay. Great. How about yours? Perfect. Done. Excellent. Okay. Here's the cool thing. This line is almost the same as the first line. What's different?
0 and 2.
I don't have an f of 0, and instead I should have an f of 2, correct? And it doesn't matter what order I add things in, correct? So can't we just arrow over to where it says y1 of 0 and make that 0 a 2? Yes, we can, which saves us time. So instead of having to we don't even have to delete a piece. We just have to type over the 0 and make it 2. And we can hit enter, and then times 0.5. You can enter all this in by hand every single time if you really want to. It's not going to hurt anything. It's just going to take you longer. Okay? So what do you get when you enter all of this into your calculator? 17.5. Did everybody get 17.5? Great. Now obviously this is not going to be quite as clean or easy to do part B, right? Because on part B, I need the midpoint of every single one of these, and the midpoint of every single one of these is none of the same points as that I already used. So I don't get them for free. Let's actually figure out what that would look like for our particular function. So our area, this is part B. Our area is still delta x, which is 0.5, okay? And it's still times f of 4 different values. I mean, we're going to use these all 4. So the first thing I need to figure out is I need to figure out what is halfway here. And then here, here, and here. So the first one is 0.25. Agreed. So this is f of 0.25, or just 0.25 if you prefer. What's the second one? Halfway between 0.5 and 1. 0.75. What's the third one? 1.25, and the last one, 1.75. Now, I like this particular one. Let me go back here because it appeals to my ability to do things with quarters of dollars. All right, so if you think about this like money, you know, what's halfway between 0 and 50 cents? Well, it's a quarter. What's halfway between 50 cents and $1? Well, it's 75 cents. So I kind of like that. They aren't always that pretty of values, obviously, right? So if you're dealing with values where it's not so easy to just look at it and say, oh, I know what's halfway in between, what do? Well, you add the two numbers and the endpoints together and divide by 2. So you can find a midpoint, because that's the midpoint theorem. That's from high school geometry class. You've probably seen it there, maybe even an algebra class. You can find the midpoint of any two values by adding the two values together and dividing by 2. So if they weren't nice, clean, easy values, you could do it that way. All right, your calculator will let you do this. But using that second enter feature might be just as cumbersome as actually entering it by hand because none of these numbers match. Agreed? So I'm just going to start over and enter by hand. Do vars, y-vars function y1 of 0.25, or just 0.25. That saves me keystrokes. y1 of 0.75 plus y1 of 1.25 plus y1 of 1.75. You can hit enter, and then you can multiply by 0.5. And what do you get?
15.25.
15.25. Now, just based on our observations at the beginning, we think this is the best estimate. Is it, in fact, between the overestimate, which we got from the part C, and the underestimate that we got from part A? Yeah, it is in between, so that's good. If we had gotten a value that was not in between those, we should sort of be concerned that we did something wrong. So this number better be somewhere in between. Okay, and just for fun, I'll tell you what the actual area is. We'll just let the calculator do it for us. Is it 15? It is. It's 15 1/3. So 15.333 is the actual area, which we'll figure out. Don't look, Darby. It's okay. I promise. Don't be concerned where we got that from. We're going to do that in the next class session, and your calculator can do it for you too. But the actual answer is 15.33. I mean, 15.25 is awfully close, right? And that's without using any calculus. What you just did in this section did not use calculus. You didn't use calculus in the last section either, by the way, right? It was addition, subtraction, multiplication, division. Yeah. So same thing in this section. This is the foundation steps for the calculus that we're going to be using in section 4. Any questions on this one? All right.